with a presentation entitled A Case Study in PB 210 Dominant Contamination. Simon is the Principal Advisor at Radiation Services WA. He's had a passion for radiation since the late 90s, and he currently holds a number of Radiation Safety Officer or RSO appointments in Western Australia and the Northern Territory. Simon also took up an appointment on the National Executive Committee of the Australasian Radiation Protection Society, SNAFL, in 2021. So please welcome Simon with a case study in PB 210 dominant contamination.
Thank you. Thanks, Kirsty, and thanks to you all for having me. Very interesting. I've been trying to get along here for a little while now, tie in a bit with Dean Crouch and a few others, and have heard a lot about you. And I'm certainly not going to do a strong push today, but the whole ARPS thing, we see a few synergies there as well. The way I see myself, I suppose, is as a radiation protection professional. A lot of different names going around for it, a lot of different buzzwords, as I'm sure you guys have in your industry. But I certainly see that there's a lot of collaboration, a lot of cross-contamination, let's say. I just made that up on the spot. Should have thought of that earlier. Between things like hygiene and radiation protection. And I certainly see radiation protection as a very specialised subset of health, safety, environment type concepts as well, as hygiene is in terms of managing health. I've probably changed the twang of this presentation a little bit, to be honest, but Lead 210 has a nice little spin to it as well, but there's a few complexities to that, and there's a bit of work behind the scenes that Alana, Lauren and myself are doing, and it's an evolving process, but we'll see how this goes. So a little bit about myself. I said before for the icebreaker that I want to be a chemist, and that's flowed very well into these guys' hands. They apparently grew up that way. Only because maybe physics just, I don't know, I guess I work in physics. I'm one of the rare people that has converted it into a job. And actually that's one of the big pushes we're trying to do, is to get people into radiation protection. So really interesting to hear Lucy's thing. You get this certificate, how do you get there, what's your pathway, but then what do you do with it next? And so we're trying to... So I was at Radiological Council. So my passion, when Kirsty said late 90s, was probably mainly from mucking around with stuff in labs in the physics degree here, funnily enough. Worked for the regulator for 5-6 years, Radiological Council, focusing on industrial radiation safety. So as opposed to the medical side, we were focused on mining. Oil and gas was starting to become something on the radar then, although it was under the radar, if I'm completely honest. And then just general industrial stuff, so construction and other bits and pieces. My other hat that I wear is in emergency management side of things. I've got a pretty unique blend of things going on there, and I kind of like the Lego man up there. I think I found someone that had it. I can't remember who it was, but I thought that kind of ties me together a little bit as a hazmat type person and a radiological, I don't like to use the word expert, but I guess that's one of those things you throw out there. So yeah, that's a little bit about me. So in terms of, I wanted to tell you a little bit about myself, and in terms of what I see, and I think you guys being here are probably all quite passionate about what you do as well. And what I love to see is to break down, and I'll get into it a little bit further in a second, is to break down the languages and to try and communicate clearly, to have people understand, to not overreact, to not underreact to radiation, which is a very fearful concept. So in my mind, where does that come from? Things like outlining clear responsibilities, things like registration with the regulators, whether that's, and we'll get into DEMERS or Rad Council in a minute, and of course their consultation and approval, things like licensing and how you get to that point, radiation management plans, and then all of those things come together. In my mind, the personnel and the consultation with those people create that safe system of work, and all the other things fall out of it. The management plan is a critical component to that, to then articulate who is responsible, how are we managing it, what level of training have they had, and all those other things. And I'll give you a few quick examples about why, how that can go bad, I guess, or how we see it come up a little bit. And I guess, again, it's just this word radiation has a negative connotation. If you look it up in a dictionary, if you Google it, whatever you do, it's a bad word. And clearly you can see me because of visible radiation. We don't differentiate often between ionising and non-ionising radiation, ionising being the harmful stuff as we see it. And I guess in my mind, is everything harmful? Maybe it is, but maybe it's not. And in my mind, it's about trying to get that communication of risk right. So unfortunately, radiation protection, I'm not hugely au fait with hygiene, I'll be completely upfront. But I'm sure you guys, as well as us, we have these words that are just so complex and they might have dual meanings, and you can't just take it on its own. You have to understand all these other things before you can use that word or use that concept. So I'm really passionate about trying to communicate that stuff clearly, to simplify it and to use plain language as and where we can. Quantifying that risk is obviously critically important in terms of saying, we go out to some sites and people are just completely apathetic, don't care at all, throw the stuff in the air and breathe it in for all they care. Other people don't want to go anywhere near it as soon as you mention that word or you see a trefoil or something else goes on. So it is absolutely about quantifying it and getting that concept right. A graded approach is a bit of a throwaway line in terms of radiation protection, but it's a really important concept, is that in particular with regard to training, and Paul could speak to this as well, in terms of what level of training does someone need to become an RSO, a radiation safety officer. I'll try not to throw too many acronyms at you tonight, but if you're an RSO, a radiation safety officer, what level of training, experience, competence do you need to do that job? You might have some underlings, we need some mentoring. Most people don't even know radiation protection is a job, a vocation, a field that you can go into. So we need to groom people to come through that and mentor them and build them up as well. And of course, we're all, I'm sure the same as the people in the room, we're always learning as we go, always things going on. Qualifications is an interesting one versus competence. Sometimes we want that bit of paper. I think hygienists and radiation protection is a very complicated discussion in it at all. I guess what I'm alluding to here is the fact that they're often after a hard science degree, a STEM thing. So someone that's, I'm just trying to think of a better example in terms of someone that's not necessarily qualified. Let's say someone doesn't have a bachelor degree in science. They might still become a competent person by doing postgraduate work. They might have a huge amount of experience in their field from however they've gained that. And then I would argue sometimes that person is excluded because of their lack of something as simple as a science degree. We might be missing out on a whole bunch of competent people because of such things. And then again, that radiation protection is a career thing, which I won't bang on about. I'm sure, like you guys, you're always trying to put things in perspective in terms of the hazards and the risks that you're dealing with. And this is just a throwaway slide and setting a bit of context here. With managing radiation, sometimes there is a safety risk. Sometimes we can, and I love to use the words acute and chronic. We use funky words like deterministic and stochastic and somatic and all this other rubbish. But in my mind, when I'm talking to someone in simple language, they can kind of get the acute and the chronic effects. Sometimes, yes, we can see acute effects of radiation. That is absolutely possible. The stuff that I'm talking about today, you pretty much can't. When you're talking naturally occurring radioactive materials, you're managing their health. Actually, Wayne might have given it to me back in the day, is that you're managing someone towards a healthy retirement. You're looking at that delayed effect. You're managing, other bits and pieces, indeed. You're happily retired, indeed. Whereas you put all these other risks out there, and of course we look at risks or we look at hazards. Is it an unmanaged hazard? Does it have controls in place? I'd suggest anything radiological, if you compare it to these other things, whether that radiological risk is controlled or uncontrolled, it's generally probably less than surface mobile equipment running around. Even light vehicles, driving and vehicles are always at the top of that list. Whatever cylinders is, I don't know what that coloured cylinder might be. Compressed gas is nitrogen, is it? Confined space. Obviously, we've got radiation, dogging, rigging, lifting, heights, all these things. Absolutely, a lot of that stuff can kill you, and radiation can as well under certain circumstances. But let's get it right, is I guess what I'm trying to portray in terms of where my passion comes from, I guess. This is the classic that we get. We get every week phone calls about these things. Can I just come and hire a survey meter? And of course, we say maybe. I'd argue sometimes it would be negligent to give that person a survey meter and they go off and they don't know what they're doing with it, and they don't know where their blind spots are with that meter. They might have a really weak radiation that's being emitted. They've got the wrong type of survey meter. The numbers are 0 on the survey meter, so they think they're fine, but maybe they're not. Very, very common query for us. The big one we get is, I'd love to become an RSO. Can I come and do some training? What we need to do is to say, an RSO for what? You could be for dealing with radioactive ores. You could be dealing with X-ray apparatus at the airport where there's really no training required. You could be dealing with a non-destructive testing unit which pumps out huge dose rates, and you need a very different level of training and competence to achieve such things. Really common question again on the back of that survey meter is, actually I had someone say this to me last week, I waved the survey meter over this thing and I determined that it wasn't radioactive. And I said, cool, I don't reckon I'd be able to do that. I challenge that you've got that right on this occasion as well. They're very distinctly different things. So we need to understand that there are complexities to it, as there are with your trade. It's just one of those things. Arm yourself with the right information, get the right people, and work down it that way. I did want to set the tone a little bit because I've certainly had the brief to keep this high level, and I'm trying to keep it interesting. We want to make radiation protection sexy, for want of a better word. Try and get some nice pictures up there, get people interested. Yeah, keep things moving along. However, we need to kind of understand that a couple of the bits of terminology I'm using here are that we might have a source of radiation. So in this case, that's a rock. It might have elevated levels of radioactivity to it. So that's what we talk about in terms of, we're saying that's radioactivity. What do we measure radioactivity in? Typically in becquerels. There are some other things that we might use there. But equally, a source of radiation might be an X-ray tube, or it could be a sealed radioactive isotope that's in a processing device, whatever the case may be. Very, very common that people mix the words radiation and radioactive together. They use them interchangeably. They're absolutely not. Something that's radioactive and decaying emits radiation, and then that radiation is ultimately what we're managing. So we're looking at it from a health perspective, safety perspective, environmental perspective, and all the rest of it. But they're very different concepts. And flowing on from that, and I've stolen these diagrams from, this one's from Japan, I think. Ultimately, when we're dealing with that rock, if we put that rock in a sealed jar, let's say, we might only be dealing with external radiation then, because we've got no risk of getting chunks of that rock, chips, dust, whatever that mobile type of substance might be. We're keeping it external to us. We've already got a certain amount of radiation that we're being exposed to anyway, but essentially if I leave that rock over there and move over here, I'm getting no exposure from it at all. If I start grinding and pulverising and chemically processing that rock, then I open up all these other pathways here in terms of your typical ingestion, inhalation, etc., that we all know about. So typically we talk about internal and external exposure pathways, let's say. So in terms of what we wanted to talk, well, what I wanted to talk about here, hopefully you're interested in listening as well, but in terms of the journey we're on, we were looking at a decommissioning project recently, and I thought I'd talk through a few of the complexities that we saw here to give it a bit of a real life story rather than just bullet points on a page that have no context here. So essentially we've been dealing recently, for a little while actually, about a plant, rare earth operation. They're looking to decommission a part of their plant, a hydrometallurgical plant. And what does that mean? Essentially, they're looking at doing some metal recoveries from that rare earth. So they're looking at dissolution, concentration, purification. I couldn't tell you exactly what those words mean. But essentially, the things that jump out at me is that they've got a kiln there, which is heating things up. That can change the behaviour of what we're looking at. They've got a leach process, so they're trying to dissolve bits and pieces through there, so that changes the chemistry a little bit. And they're mucking around with pHs and pushing things in and out of the process in different parts, and so it creates a very complex scenario. So they want to get rid of a part of the plant. It probably is about there where I'm drawing actually. They want to get rid of all of that and send it to somewhere else in Australia, and so we've got cross-jurisdictional problems with this as well. It just so happened that I think the first letter that went to one of the regulators happened to say, oh, we're just going to, we're going to do a gamma survey on this and we'll make sure there's no contamination. And that, funnily enough, got Paul and Martin's back up a little bit and saying, I don't know if you know exactly what you're going to, you don't have the full picture if that's all you're doing. And if you've written just that one line, maybe we need to look into it a little bit heavier as well. So we pressed pause or expand or whatever at that stage, and started helping out a little bit. I suppose our scope on this job, and I think this is quite transportable in terms of our priorities, is that clearly one of our charters, and as you can tell I'm pretty passionate about this, is managing the health and safety of the workers and community and environment and everyone that's involved within that. So we're managing exposures basically to them. We're minimising that as much as what we can. Sorry, I've chucked an acronym in there already. I presented this recently and it was to a whole bunch of peers, and I got a lot of good feedback as well actually, but now the acronyms are not so relevant. SCO is surface contaminated object. So basically it's an object where you've got your bit of pipe, your vessel, your whatever it might be. It's made of metal or fiberglass or something. It's not radioactive, but something is on it that is potentially radioactive. So we need to then consider that object. So managing SCO is probably well, it's not the most important part of this. The most important part is managing the radiation protection of the workers. However, to clear this and get rid of it, particularly across a jurisdiction, we need to make sure that it's not contaminated, because that's going to cause an issue elsewhere down the track. And then, of course, within the process, actually you can see whole lots of bits and pieces lying around. There's naturally occurring radioactive material. That's the NORM acronym. I apologise for that. NORM is through the process, so it might be in the bunds. We're certainly getting it off the pipes and things so we can get rid of them, but then we need to manage that stream of things as well. Get my button right. So how do we do that? Often I'd get a process flow, something like this. This is actually on a bit of glass on top of a table somewhere in a meeting room, and I draw lines all over it. None of it will mean anything to you, but it was quite interesting to me because I'm looking at where the solubility type concepts might be. We thought we had it all nutted out, but then we figured out that they're actually putting the concentrate ore back in at another stage. So then you've got a couple of different streams coming in that cause different problems for us. And I guess that's outlining the problem we were facing. And then I'm going to try and talk you through how we went through a discovery process, I suppose, to solve it. So certainly that's the first thing we're doing, is discovery and defining of what's going on. What history do we have there of the site? So I'm talking about the numbers, the workers, the people. Were they doing their dust monitoring? Were they doing their surveys? What data have we got there to show what it could and would have been back then? And then, of course, what is it now? So we had a bit of historical data. The plant has changed a few times, and we needed to figure that out. We had to come up with some systems of work, or proposed systems of work at this stage, and then, of course, get regulatory approval. So that's to do with the stuff on the previous slide. How are we going to manage the objects themselves in terms of clearance? How are we going to ensure that we're keeping those doses to all the workers as low as reasonably practicable? We need to have a plan that articulates all of those things. And then, of course, we had to try and put that into practice to say, you know, this is working. We think we've got this laid down. So in my mind, it's a complexity. I'm not complaining about it. It is what it is. But we have different regulators in Western Australia. So some of the background here is that, so I'm ex-Radiological Council. That's where I was. I'm very used to dealing with sealed sources, X-rays, and we dealt with NORM mainly outside of the mining space. So oil and gas NORM, it has nothing to do with DMIRS, being the Department of Mines, Industry Regulation and Safety, but it's a very similar concept, but very different regulatory liaison, I guess, in terms of who you're dealing with there. So in this case, given its NORM from a mining process, the primary regulator is not Radiological Council as we deal with in oil and gas. The primary regulator is DMIRS, and then of course most of the time what they say, I hope you agree, Paul, but most of the time what they say as experts, Radiological Council typically follows suit with, because that's the pecking order of things, if you like. There's certainly a lot of consultation and collaboration, I'm sure, or there certainly was back in our day. So again, a bit of a simple statement went through to the regulator to say, hey, we're getting rid of this thing. And there was a bit of a query of understanding came straight back to say, do you really know what's going on here? With radiation, as you guys would well and truly know, I don't need to explain detection versus measurement. You might know you might see a little bit of something's there, but how do you know how much is there? There's a lot of extra steps you take to make sure that you know exactly what's going on when you're trying to measure something. And this was really quite difficult to figure out how to measure. And I'll be honest, I don't even think we've got it knuckled down quite yet either. And then, of course, with those surface contaminated objects, what should we apply? Now, the ultimate complexity here is that so some of this plant does have a lead-210 dominant contamination, and I'll explain a little bit more about that in a second. But the problem with this is that, let's see if I can get this right because I'm not completely familiar with this diagram, is when the lead-210 decays, it's emitting gamma radiation, very similar to X radiation, except it's a very weak gamma, very hard to detect. If you had something that was lead-210 dominant within your process and you're measuring on the outside of your process, you might not even see it at all. The thin metal, let's say 4 millimetres, 5 millimetres of steel might be enough to block those really low energy gammas being emitted by lead-210. Decays to bismuth-210, that's a pure beta emitter. Beta's difficult to detect as well, certainly not very penetrating. And then alpha radiation, where am I circling here? Polonium-210 is an alpha emitter, and that you won't detect at all. A couple of centimetres of air will block that very, very easily. So I guess that was a fair question to say, where are you doing this gamma monitoring? If you're just running it down the outside of your pipe, you've got no idea what's going on. So which surface are you looking at? Simplest of questions to answer, but then we'll get into some more complexities as we go. So of course the big button was pressed. Let's take some more time, let's consider this, let's have a bit of a look at this from a step back type perspective. So in terms of one of the first ports of call was to get up there and get some boots on the ground and get some data, grab some samples, grab some information as best as we could, lots of process flow analysis and seeing where things were going. And then of course we wanted to define what we were trying to achieve here. How are we going to do that in terms of processes as well? This is why it's complex, I guess, is that we've got three distinct decay chains, if you like. This one's from uranium-235, often called the actinium series. We don't focus too heavily on that, really low percentage out there in nature. But in this uranium decay chain, you can see there's a lot of complexities that exist there. The main ones of interest, I guess, are that with the radiums, and you can see there's radium in the thorium decay chain as well, but radium's just a very soluble element, let's say. Yep, there are isotopes of radium, and every time it is radium, it's going to be soluble. Radon's a gas, noble gas, can't filter it. That starts to migrate through in different processes. Something really quickly while I've got here, without getting too bogged down, is that radon does migrate very smoothly, very easily. However, all of these are very short half-life substances until you get to lead-210. So this stuff may have been there, but after a very short period of time, it's all gone. And then what you're left with is a lead-210 issue. That decay's got a 22-odd year half-life, something along those lines. And then that's decaying through to bismuth and polonium, which are the ones I just described then. So what we need to figure out is, well, let me just say, in nature, if something's been there for a period of time, uranium-238 has a 4.5 billion year half-life. Tim, got that right? Yep. Ultimately, it's going to be there for a very long time, but also all of these are in what we would say secular equilibrium. They're all in the same amount of activity in perspective to each other after a period of time has passed. Once we start mucking around with that, with leaching, with heating, with different migration processes, we can end up with different equilibriums, different heads of chain, if you like, or different elements of there are different components of the pathway in terms of how they exist. What's the head of chain? And head of chain's not even really the correct term, but what's the head of that problem that you're seeing there? So what we have known, and this is in particular, oil and gas is really across this, and mining's certainly fully aware of it as well when we've got these other processes, is that as I mentioned before, the radium can come out particularly with leaching and with water and with other hydrocarbons and other things, or in particular we're talking mining here. As we said before, radon can migrate across this way, and there's something funky going on down here that, from my understanding, we haven't quite got to the bottom of it yet, is that we talk about an unsupported lead-210 chain, where potentially unsupported means the lead-210 isn't coming from all this up here, it's its own entity down there, and it's got its own little subset or sub-chain that's going on down there. And we're not sure exactly why polonium would be out of equilibrium or lead-210 would be out of equilibrium when it's not supported by some of these other ones there. Similar concept in the thorium decay chain. So certainly we've still got some radiums. They're different isotopes of radium, but radium nonetheless. So chemically, when we look at elements, they react the same way if it's the same element, but the isotopes of those elements, meaning a different number of neutrons, basically we end up with, sorry, why didn't I throw that back here? We end up with different concepts radiologically that we don't necessarily see chemically. So the radium will behave the same way as what it did in the uranium chain. Radon's there as well. However, they're all very short half-life substances after that, so we don't generally focus on this chain quite as heavily with regard to the disequilibrium. Now, in terms of gathering history on this site, there was a study done by ANSTO, another acronym, Australian Nuclear Safety Technology Organisation. They're the ones that run Lucas Heights Nuclear Reactor over in Lucas Heights in New South Wales. They do a lot of industrial stuff as well in terms of consulting and advice, and they've got some really ridgy-dig scientists there. They're good at what they do. They did a study back in 2014, and they started looking at how does this flow go in terms of what drops out in different parts of the process. But unfortunately, what they were looking at was the product going out, not our problem, which is the contamination, in terms of where might something build up and how do we get rid of it when we're trying to get rid of that at the end of life. That wasn't even a concern for them back then, because they were looking at production. There was a slight change in the chemistry that they were using an oxalate, I think, and now they're going to carbonate. Doesn't mean a huge amount to me, but essentially we needed to figure out whether that was going to be a factor or not. What that study typically found was, as per the previous slide on oil and gas knowledge, all this other stuff that goes on, we certainly saw a lot of radium rejection out with the leaching. Just makes perfect sense. You see that solubility, it's going to go left and exit out that way. So we saw a lot of that go into the tailings part of the process. But clearly through that part of the process where that leaching is occurring, you'll see some interaction between the product that's going through there, and particularly because a lot of it was actually pH of 1 or something like that, super acidic type stuff going on in there. Basically what we're looking at is that interacting with the pipes, with the vessels, with the processes when that kind of stuff is happening. We certainly saw disequilibrium towards this lead-210. What we didn't foresee coming and didn't look into and wasn't really mentioned in this study is that a lot of the back blending back in to achieve more output from the process that happened later in the plant, then we're going to see potentially some of the lead-210 go through, but then a whole lot of thorium dominant stuff is coming back into the process. So we might see an absence of it here because it's gone a different route. It's gone right rather than left, or whichever way I made that acronym up, that analogy up. But we saw different problems come back in later. And one of the really big ones that was questioned, I suppose, was within ANSTO, they suggested that we had no understanding of what the polonium-210 was doing. I'll talk again in a second about isotopes that are easy to measure or difficult to measure, and that's a way that the international community is going, I guess, is breaking these down to say we can pick up some of these, but other ones are just really difficult to analyse for and to find out. Lead-210 is not overly difficult to analyse and look for. However, it's a bit expensive and it's not a common practice that we go to look at. And sometimes I would question the logic as well. As I've said, was it previous slide? I didn't get burnt too badly. Sometimes we see an unsupported equilibrium, but it's not overly common. Most of the time it's reasonably predictable to say that it should be in equilibrium with the lead-210 in terms of the understanding of the process that's occurring. So what didn't we know? As I said a second ago, different parts of the plant probably had different layers of isotopes going through that we might find a lead-210 dominant problem here, dominant, or this might be head of chain being uranium and thorium dominant. Another point I should raise straight away is that often these plants, they're mining ores that are maybe slightly elevated in uranium and thorium and all the other stuff below it, but where the problem really comes out is that they're targeting certain elements out of that process, and so in doing their processing, they're concentrating some of these radioisotopes of interest and therefore bringing them up to levels where they absolutely are subject to, we basically would say something is exempt or subject to regulatory control. It has the potential to cause harm. We need to manage that, we need to manage that process in terms of how it's being dealt with. A question that we're asking straight away is to say, well, it's pretty easy to grab hunks of sludge and dirt and scale and things and analyse that. But is there a connection between saying that what we're finding on the pipes as contamination, is that the same as what you're finding in terms of your process, your sludge? It might react differently to, for example, stainless steel or fiberglass. There's going to be a different chemical interaction that's taking place there, particularly when you're mucking around with really acidic stuff and then trying to balance that back to a more neutral process as well. One of the really big questions that we're going to explore coming up is whether the contamination we're dealing with is fixed or non-fixed. Non-fixed might mean that you can physically see something caked on there. You give it a blast, a bit of movement with some chemicals, whatever you want to do to it, you might be able to move that stuff along, but we might get to a certain point after a few iterations of decontamination that something is stuck there. It's chemically bonded in with the stainless is a classic one for it. Yep, and we might not be able to fix it there. And arguably, I would say if something is fixed in terms of contamination, the risk must be hugely minimised. Yes, there'll be some external radiation from it, but typically that's quite a small component of the pathway, your exposure pathway, compared to mobilising that scale of stuff, particularly with things like grinding and hazardous part of the process, and mobilising it and then breathing that stuff in, or not having your hygiene up to speed and you're ingesting it because you don't have a hot and a warm zone, or you're not washing your hands or wearing gloves or other things. So in terms of how we figured out where we were aiming, there's some guidance applied or given to us, I guess, from a set of WA norm guidelines. They were produced by Department of Mines and Petroleum back when they were called that, 12 name changes ago, whenever that was, I'm not sure what year. And I think we're pretty unique with that in terms of around the world, from what I've seen, and certainly around Australia, we don't have these complex sets of how to do things. It's a really good how to do it type set of documents, if you like, in terms of how we work with that. And we've got RPS2 is Radiation Protection Series document. C2 is a new version of a transport code of practice based on international regulations, but certainly adopted here throughout Australia. Actually, I must say C2's only just been adopted a couple of years ago. It's been around for 10 years, but it took them a long time to get to it. But we've had a different document in place that had the same thing. So those those documents do have numbers within them. And specifically what they're saying is, so remember we said becquerels is how much radioactive material you've got? So what we're looking at here is how much radioactive material do we have on that surface per square centimetre is just an arbitrary per unit measurement that we have there. So the numbers are different if you're dealing with beta or gamma emitters or low toxicity alpha emitters. And these are reasonably well defined in terms of what's low toxicity or what's high toxicity. Actually, there's something else in there about a half-life less than 10 days, I think, that goes into that concept as well. So I guess the question I'm asking here, which I skipped over semi-intentionally, is what was the intent of those numbers? And the more we look into this, the more we get to say, well, actually, I found a statement in the recently that said that the numbers so these numbers are the same in the norm guidelines and in the transport code of practice. And my understanding, which I didn't realise up until recently, was that those numbers were developed in 1961, I think. I'm sure I've got the number in here. Radiation protection's changed a lot in the last, I won't do the maths on how many years that might be, 61 is it? 61. There you go. Oh, you're that old, yeah. You don't look at Tim. So we've changed a lot in that period of time. What is the intent of them? Is it when you're transporting something along the road, if it's typically designed at a package, it's something that's packaged, whether that's bulk and sealed, whether it's got caps on it, whether it's a box or a typical consignment that we would think about. And essentially it's about what's the possibility of something becoming mobile or mobilised that it might become an exposure pathway to us. That's probably the ultimate intent. I've made that up completely, but that's my paraphrasing of what the intent of those numbers were. So I guess what I'm trying to figure out is, are those numbers appropriate for clearance? Actually, this Swedish study I've found made an explicit comment to say those numbers are not appropriate for clearance because of all this other concept. What we really need to look at the end of the day is what is the health effect of this? What is the risk? It's pretty much as simple as that, and there's some numbers coming up that I'll throw at you as well. But Another concept here is that each isotope has one of these numbers assigned to it typically. Is it a 0.4 or a 0.04? That's cool. But as per that big complex thing we threw up there a second ago, we've got 14 in the uranium decay chain, we've got 10 isotopes in the thorium-232 decay chain, and ultimately we don't ever find them, what we're dealing with, in isolation. Then we throw in disequilibriums and all sorts of other concepts there. So the question I would ask is, what do we do now that we've got all these different ones? Do we go with the most conservative number of 0.04? Do we come up with something else? Can't remember the presentation well enough. Oh, good. Okay, I threw this in. This was the this afternoon effort. Here's something that we can apply. We've talked about becquerels being how much radioactivity is there, a unit of radioactivity. We've talked about becquerels per square centimetre, how much is on that surface. What we're talking about here is becquerels per gram. This is activity concentration. So you might say, let me just say this, is that a lot of naturally occurring dirt, rocks, whatever you're talking about, concrete, other stuff that we're building, has uranium, and it's at low enough levels that it's not of concern to us. It won't contribute to adverse health effects. It's below regulatory exemption limits. When you get above, typically with our norm concepts, we're often applying a 1 becquerel per gram exemption level. It's not as simple as that, but let's just keep it at that for now. We're looking at saying how radioactive is something. You guys might have talked about things like, I'm just trying to remember, grades would be a simple word for it. I can't quite get the word out of my head. But things like grades of ores, where we're measuring something in parts per million, you can correlate that across using a specific activity number, essentially to work becquerels per gram. Us radiation protection people would use becquerels per gram. Your geologists and your people making decisions and your metallurgists would often be using ppm in terms of the higher the grades, the more value they get out of it. Typically, the more hazardous it is to us as well. So if we're dealing with a mixture of radionuclides and working out activity concentration values, that's reasonably well defined, that we might look and say, what percentage is it? In this case, we're saying it's 75%. I can't remember what these isotopes were, to be honest, and it doesn't really matter, to be honest. But we've got 75% of this one at 1 becquerel per gram, 25% at that one. Do a bit of a funky calculation, spit out a number, and you end up with one number in becquerels per gram that combines those. From what I can find, there's no equivalent value in the literature, and I'm happy to be proven wrong. I love to be proven wrong because it solves a big problem for me. Yell out. But it appears, well, I would argue we can apply a similar principle to surface contamination limits, but it's arguable as to whether you can do it. And clearly the ultimate question is that acceptable in terms of the risk that it's portraying, and who makes a judgment on that risk? Clearly we do it as radiation consultants, but equally the owner of that risk has a charter to be doing such things, and the ultimate question is, will the regulator approve with this rationale to get to that point? Because of course, if the regulator's full of experts, as we've got a few in the room, they need to be on the same page as well. If we come up with some humply-do stuff and it doesn't make sense and gets challenged there, it's never going to work, clearly. We would like to think that anything that's being done in this industry is repeatable, defendable, and based on fact and evidence, I suppose. We did actually get an endorsement doing exactly that with some waste that was lead-210 dominant. In oil and gas, we very much see a very defined. Sometimes the uranium and thoriums get transported through in sludges and solid materials, but we do see a really big disequilibrium with radium. We can often prove that it's in equilibrium from radium down to the lead-210, but then from lead-210 onwards, we prove that that's an equilibrium. And so we did something exactly the same as this formula, applied that and come up with a few different numbers here. And in my mind, that made sense. Is it completely bulletproof? No. Is it completely robust and peer-reviewed and all the rest? Definitely not. However, it's frustrating, I guess, when you can't go and find numbers to work with. No matter where you look, I got pointed at Malaysian studies, and I just quoted a Swedish one, and everyone around the world is doing different things. I'd love to see, not necessarily numbers, I can't find numbers, that'd be great, but even a methodology to work these things out would be really helpful for us to work with. Now, that's the behind the scenes complexities, but when we're out on the ground, how do we actually determine that? I'm not sure how much you know about radiation survey equipment, but basically this is a common device used in the oil and gas industry. It's actually got some pre-programmed modes for radium dominant stuff, lead-2 dominant stuff. You can get these numbers out as well if you push the manufacturer hard enough, although they won't give you a thorium-232 number. However, these will behave very differently. This one's a scintillation type device. This is a Geiger-Müller type counter with a window. Certainly that lead-210 dominant stuff that we found up on site, we were getting 0 radiation readings using that. It's a really sensitive device, amazing device, bloody expensive. I hate to think if one of our people dropped it, but it's showing 0. There's no risk there according to the numbers that you're seeing from that probe. But all of a sudden, if you put this probe over it, the right probe, the right instrument for the right job, it's screaming and giving us some good numbers there. But we need to know what what mode we have it in. We need to know what we're doing with it. So the selection of the right equipment, but then there's how it's used as well. That's another complexity that we're dealing with. So what do I want to say there? So the concept is that a radioactive decay happens, radiation is emitted. This detector is what's the word? It's interacting with that radiation, and then it's simply seeing an event happen. It's got a little electrical impulse, various things can happen on the inside there, and then it's calibrated to get that little electrical signal out to a number that means something to us. We can put this in any different mode we want. I had someone last week actually giving me contamination on surfaces in counts per second, which is, you can't deal with that. It just is never going to work. Unfortunately, yeah, I won't get into it. I won't get into why. Their background was in counts per second for contamination as well. It's really confusing. What we need to do is to figure out the efficiency of that, and that's what we're looking at here. So the efficiency would be either becquerels per square centimetre per count per second, or vice versa in terms of which way you equate that efficiency. There's huge amounts of it. If I'm holding a radioactive source, it's emitting radiation in all directions, obviously, 360 degrees, we'd call that 4 pi. But of course, your radiation survey meter is only going from one direction, so automatically you're missing half of it. So a radiation detector is typically only, 50% is kind of a maximum in theory, and of course you're not getting all of that radiation either. So there's a lot of complexities to how it goes. But essentially it's a pretty dumb device. It needs us to input the mode correctly. It needs to say, well, we're saying, are we wet or are we dry in terms of the material we're measuring, because there's self-absorption between some of this radiation that's occurring there. And then of course we're I wouldn't say we're assuming, but we need to know that the material is lead-210 dominant contamination before we're using it in lead-210 dominant mode. Otherwise the numbers won't be accurate. If that, it sounds logical. I'm sure you'd agree with that. What about something where we've got other dominances? So I'm talking about the thorium coming back in. We've already got a lead-210 thing here. We need to start looking at that again. It's going to be really hard. This is the quote I found. Oh, I even got the year right, Tim. Were you born then, did you say? Yes. So this was a quote from a new IEA document. It's in a draft mode, talking about clearance, and I'll talk about clearance in a second. But basically it's saying, therefore, we shouldn't be using these numbers for clearance because they're based on something else. They're based on ultra-conservative measures, which is good. We always start ultra-conservative, absolutely. That's the best way to go. But clearly, the more conservative we get, the more prohibitive we get in terms of releasing stuff. And ultimately, where this document's aimed, that I'll bring up a few other little things here, is about reducing the regulatory burden as much as we can. And that's on the regulators, that's on the people using it, disposing it, whatever, anyone and everyone involved in it. And of course that has to be defendable. So that's a bit of the background. Here's some of the stuff that we found when we went out on site. Here's some of the observations we had. You'd sort of see, this is an agitator. This is, I can't remember exactly what tank this was in, but often you can see a whole bunch of crud that's on it. That's pretty good for the guys out there because they can see it. They can feel it. They know to put gloves on and other stuff before they're touching it. It's clearly in their eyes. However, I'll go out on a limb. Here we go. Same process, different agitator. This one looks crystal clear. You can see a few little bits and pieces on there. But ultimately this had quite a lot of lead-210 contamination on it, and the other isotopes that are there as well. But this to me is a risk because people can't see it, they can't feel it, they don't know it's there. And it's about getting that risk, I guess, right in terms of saying, are they dealing with it appropriately? Not going too heavy with the health and safety side of things, and also not being dismissive of it. It's getting it right would be where we're at. A lot of this contamination just wasn't moving as they were trying different bits and pieces to move that, and we had a whole lot of different types of plant construction, which I talked about a second ago as well. So how is these different product streams going to react with different parts of the process that we're dealing with as well? And I guess that's where we're there. Oh, one of the big ones about the new rules. People are saying, why are we doing, you're up here, Mr. Radiation Protection, why are we doing all this stuff now, all of a sudden? I'm saying, well, actually, you probably should have been doing it the entire way along. It's nothing different. The hazard hasn't, well, actually the hazard did change. I'll give them some credit for that. Because obviously we're starting to pull things out now, but that's not probably enough. You know, they might be changing a pump impeller every now and again. So in reality, they would have had that hazard there. It's a bit of a cultural thing in terms of how we, just because we're changing something now, I hate change for the sake of change, but just because we're changing it doesn't mean you were right in the first place or wrong in the first place. It's about getting that whole continuity and picture happening as well. Where were we aiming with this? This is a bit of an older slide, to be honest, but essentially we were looking at that workforce. Clearly the boots on the ground people, they're dismantling this huge plant. God knows how many tonnes are there in that process. We need them to have some level of understanding of saying, just because something looks clean doesn't mean it's not a hazard to you. We need, the survey meter is ultimately the tool that's going to tell you, is there a level of contamination there? And don't get me wrong, when I started talking about other hazards that were out on sites as well, I've already mentioned huge amounts of acidic stuff going on here. Clearly they're disassembling something, so there's different dogging, rigging, all sorts of other hazards there as well. This is just one of the things that they had to try and get their heads around, I suppose. I guess talking about hierarchy of risk control as much as not relying too heavily on PPE, it's probably the same as what you guys do. Such a simple process of dealing with, if we look at old mate doing a measurement here, you could put gloves on and you could handle that and do all the other stuff, but if you don't have to touch it in the first place, of course you're not exposing yourself to that hazard there that is physically getting that material onto your gloves or person or whatever and introducing another pathway. So thinking up that chain of control there, could we build stuff? Could we build stuff to control the risks? Could we go higher up that hierarchy of control rather than just relying on PPE and administrative controls? Another throwaway line would be that finding that radiation is really simple if it's in the right place, but as per all those other complexities that I've talked about over the last few slides, actually measuring and saying here's the number, particularly in a number that is towards us saying this is not hazardous and therefore would be, well, actually I'll argue a different viewpoint in a second, but essentially saying something is this many becquerels per square centimetre, how do you know that's the case unless you have all these other inputs to it lined up and understanding exactly what's going on? One of the other hazards out there, I guess, is that the external dose rates are really low, and we find that with Norm a lot of the time. You could stand there for thousands of hours and you're not going to get a huge dose, but clearly if you go and start licking this thing or getting on your hands and going over a durry or not washing your hands before you go and have a drink or something to eat, you're going to get a huge pathway from that. Very low external dose rates, and sometimes in my mind that allows people to be apathetic about it, I guess would be a way to put it. And what are they doing while they're disassembling this? Of course they're going to be cutting, grinding, welding, mucking around with stuff, so they're introducing all those pathways that are of most concern to us. While it's all bound up in their process, it's not exposing anyone to it. Well, there's a slight external radiation risk there, but they're not exposed to the inner workings of that process yet. Oops, what have I done? Oh God, it's doing all sorts of funky stuff. I don't know what's going on here, let's roll with it. When you get out there, obviously, you start seeing bits and pieces like this as well to say what different items look in what different ways. How are things being done when you're out there actually physically looking at it? Stuff that looks like that. How do you deal with that? If it's leaving site, there's an issue. Well, you need to assess if there's an issue or not anyway. So back to the drawing board, I'll try and keep this moving along. We've got a lot of local legislation and guidance that's imposed on us or useful to us, I guess, and some of these are from either camp. We've got local regulations from both of those departments there, and they sit under Acts, obviously. We've got that transport code and the norm guidelines. We have a national directory for radiological protection. That was the dream back in the day, that we might get all of Australia on the same song sheet for regulating radiation. It would be amazing. The same set of numbers, the same things. You have a simple set of regulations that says, hey, use the national directory. That tells you everything. We're a long way off it. NT's doing it pretty well. Yeah, and a few others as well. Some of them try and reinvent the wheel completely, and I won't go down that pathway, but I've seen things that I couldn't sign off in WA, but I could there, in Queensland I'm talking about, because they diluted some of the requirements of the codes of practice and other things by trying to paraphrase and redo things. It's really frustrating. It should be simple, but it's not. There's a user disposal code as well, which ties in a lot with that in terms of saying you're the user, you're wanting to get rid of it. If it's below these levels, you can do so. Because of course, something I should have mentioned is a lot of this stuff deals with the X-rays, the sealed sources, tons of unsealed isotopes. Anyone you could name. I plucked these figures from somewhere deep in my head. Is that there was 100 or so different elements that we've got. There's something like 3,000 different isotopes. So different isotopes of those same elements, we've got a lot of complexity. So a lot of those are named in these codes of practice, and norm is just one of the concepts that exists within there amongst all the medical stuff that's going on, et cetera, et cetera. There's some most of the time, when I'm complaining about different states and jurisdictions doing different regulation, I must say, most of the time we are on the same song sheet with the numbers that we're looking at in terms of health, in terms of risk, in terms of what all this is derived from. It's probably just the implementation that changes a bit. The Energy Agency is one of our international guiding bodies, I guess. They don't have a jurisdiction necessarily here, but they produce documents that underpin a lot of the fundamental things that we're dealing with in our local legislation or our local guidance. So in particular, some of the ones that we're looking at with regard to this are the General Safety Regulations, I think that stands for. I always just use the acronym, so I often can't remember what the full name for it is, I apologise. But essentially that's a safety guide that is very similar to the National Directory. It outlines a lot of the concepts that we're looking at from a regulatory perspective. There's a specific, I can't remember what this one is or even what it stands for, but essentially radiation protection and management of radioactive waste from oil and gas industry is another IEA document. That was very useful. And interesting concepts coming up these days are towards, they're using these terms exclusion, exemption and clearance and the subtle differences between those things. So exclusion might apply to something like saying you've got this whole field of dirt that's got some uranium and thorium in it. There's no point regulating that. We should exclude it from regulation. It's a pretty simple concept. Exemption is more about the numbers that we're talking about. It's below these certain trigger levels, so we can say that's exempt from regulatory control. The clearance is more about something that we're intervening and acting on that and saying that this item has been dealt with, or we've determined after a process that it's exempt from that. Yeah, it's not subject to the control as well. And then the ICRP does some stuff as well that works as these foundation documents, particularly towards doses and the way we deal with doses. So we basically went through and looked at all these things, and a lot of this underpins all of our everyday stuff anyway. It was just a slightly different concept in terms of how we're applying it here. But there are different scenarios as to how we would deal with something if we're in an emergency scenario, if we're planning that scenario, or if it's just an existing scenario that we're dealing with as well. We've got, goodness me, we've got exemption for norm. Typically we use a number of around 1 becquerel per gram for any individual isotope in that chain, whether there's disequilibrium or not. We try and use a graded approach in terms of justifying the level of effort that we're putting into it based on the risk that we're dealing with. I'll talk a little bit more about exemption and clearance there, and then of course we've got surface contamination limits that are in that GSR Part 3 as well. Sorry, when I say sorry, that's a faux pas. Completely the wrong thing for me to say. There are no surface contamination limits in there. These other ones are there, talking about activity concentration, talking about total activity, talking about minimal dose, but nothing in there as such. This document on exemption, it is in draft from IEA, talks about the fact, and I have paraphrased this first point slightly, but essentially it's saying if something should probably be exempt if we can show that the risk is sufficient regulatory control. I've removed a few other words there, but it's typically to do with an item you're looking at. And then, of course, the next one down there talks about the fact that there's no net benefit if we go down that pathway of imposing regulatory control to it as well. It's just not justified in terms of what we're doing. I'll skip that one if I'm running a bit late. This clearance document specifically does talk about surface contamination. Finally, we're seeing a lot of discussion on it, and it does differentiate between natural origin materials like norm and artificial. We're talking about characterisation, and it does then go into bulk activity, being becquerels per gram, or surface contamination. It talks about two scenarios: what's realistic or predictable, and what's could happen or might happen, but it's very low probability, which is a great thing in my opinion. We're saying, is that contamination mobilised? Because that's obviously critically important. Could we actually get some exposure from it? And then it does acknowledge that if you've got something sitting there and it's not mobile, not accessible, it could still be giving you external radiation, albeit that it's reasonably minor. But again, we're absent on these limits. There's a few statements in there talking about, so actually just tying in those concepts there, it talks about these. And again, this is a guide, so it's absolutely not legislated, it's not adopted, it's not anything, it's in draft. This is all very speculative, but it is international, well, is it international best practice? I guess in draft mode it's still being subject to peer review and things. But essentially I like the concept of this is saying that clearance should include the concept that if something's going to contribute to less than 10 microsieverts per year, it doesn't matter if you're slightly above those contamination limits, because you can justify that there's no pathway for someone to receive a dose like that. That's in a, oh sorry, that's for realistic scenarios. With a low probability scenario, we try and keep people less than 1 millisievert per year, which is 1,000 microsieverts per year. And essentially that's the limit that we impose for a member of the public, basically, before we designate them as a radiation worker. We talk about all sorts of other things in there, which is great. But what we need to look at is there are different levels if someone's trying to get the uranium or thorium out of your process versus is it just there as a byproduct. You're chasing something else, but it's there as a pain for you. Is the device you're looking at, the bit of metal, whatever it might be, is it going for scrap or is it being reused? Are the isotopes difficult to measure or easy to measure? Is the contamination fixed? And then again, what bloody numbers do we apply? Let's keep working through that. We'll keep going. Talked about that. Cool. So how do we get to the end game? I am drawing very close, I think. Is we clearly need to, maybe we don't try and decontaminate. An option here is just to call the whole thing off. That's problem solved for now, anyway. But that's an option. Probably there'll be an attempt to decontaminate and to do things. We could potentially try and argue that these realistic versus low probability scenarios in terms of mobility and in terms of how things are happening, and then we might be able to meet that concept. Actually, this is a statement from that 499 or 500 document, basically saying if we can prove that something is lower than these numbers, it meets the criteria of GSR Part 3, which says the radiation risks arising from this cleared materials are sufficiently low to exempt it from regulatory control. So there's quite specific statements in there that are helpful. How do we get this concept approved? We might just try and comply with the numbers that are, we need to find the numbers, but then try and comply with them. Actually, I must say there are statements through these as well saying in the absence of numbers, consult the regulator to try and find out what those numbers should be, which is why we're talking with these gentlemen to get those figured out. However, we've got another plan in place. Clearly nothing's happening until we get that regulatory approval, not to give anyone the heads up, but clearly we need management to accept this proposed, maybe we don't. We might have an alternate way of trying to propose to deal with it. That's two sets of management. That's someone releasing it. That's someone accepting a level of risk that's associated with it. We've now got 3 regulators to deal with: Radiological Council, DEMERS, and of course the receiving jurisdiction, which happens to be in Northern Territory. And of course everyone needs to be on the same page to say, yes, we accept that that proposal is a healthy and reasonable way to be dealing with it. Leaving that open there, without digging myself into a hole too much more heavily. Questions? Any questions, comments, queries?
Just out of interest, was it the PVC that lead was pretty sticky to, or was it PVC. Just in my experience, it sticks pretty well to PVC. Sorry.
So question about, I don't know if you know that for the camera, Matt, but in terms of was it sticking to PVC, I'm not sure. We haven't even really looked at that yet. A lot of the pipes were really small bore, so sort of inch maybe, probably not even worthwhile selling, transporting that. You may as well get new PVC and deal with that on site and dispose of it locally is the way we're heading with that. I can't remember if there's any other items that are larger.
Yeah, we went through a lot of that with Esperance, obviously.
Oh, sure.
Everywhere over all sorts of materials.
And it had an affinity.
A lot of learnings about what lead was good at sticking to and
Yes.
what it was not so good at
Yep.
sticking to.
Yep. I'll need to have a look at that for sure. Clearly what we're focused on is stuff that is proposed to leave site is, well, managing it appropriately, health, safety of workers. Stuff leaving site, clearly we haven't seen, I can't think of anything that's large that we'll be looking at that's made of PVC. I think most of PVC will stay put. Wayne.
Numbers, the holy grail of occupational hygienists. everybody wants numbers, don't they? And as soon as somebody sees a number, wow, that's it. We're happy now. But there's certainly a huge lack of them, and the biggest problem I've seen when doing all this with surface contamination or anything like that, becquerels, is how does that actually translate to dose?
Absolutely.
And that's that's the crux of the problem, isn't it? I mean, if it was a nice little sort of proportionality constant, that would be lovely, but it's not like that.
No. No, and you're absolutely right. These safety guides allude to a number of international studies that do a dose conversion factor, which do exactly what you're talking about. I think they'll be very common for certain isotopes, particularly in the medical game, let's say. I think for norm, it'll be complicated, particularly when we throw disequilibrium in. It made me think of another fun analogy that we get is people freak out and say, I waved the servometer around and I got 6. Okay. Miles per hour? I don't know quite what you're talking about. What's your reference with regard to that 6? Yeah, we're probably not quite as heavy in data as you lot, but that, what do I want to say about that? It's the truth. The numbers are the truth. If they've been collected appropriately, you need to look at that whole pathway of how did you get those numbers. Was it the right sampling technique? Was it in the right place? Was it homogeneous that you're looking at? Was it sampled by the direct method? All the same concepts that you guys would have to overcome to get those magic numbers, we've got as well, absolutely.
And final point, the idea of the weighting equation that you had there, we do that.
Yeah.
You know, that's a really good, it's a reasonable approach to surface contamination or anything else really, but it's whether, you know, you're reaching the ALARA or ALARP principle, whatever. But that's a good debate, isn't it?
Absolutely. It's we've still got a few good, healthy debates going on in radiation protection. Absolutely. It's yeah, I won't even open the floor for them now. But it's always good to have that. Thanks, Wayne. Hey, Paul.
Hi, Simon. First of all, it's 7:15 and I've had a glass of wine, so this is not a regular.
Very good.
Look, one of the things with this particular situation is, first of all, it is going to get put on a truck, so it will be transported.
Yes.
So
Yep.
that ticks that box. The other thing, obviously, as a regulator, the last thing that we want is a thank you very much letter from the Northern Territory
Very much so.
government. So it is complex, but you know, it's understanding what the hazard is, and you know, and that's where it's at. So it's not just a simple matter of some numbers, and as you rightly pointed out, when you got small bore pipe, it's very hard to shove the detector up a 1-inch pipe when it's 2 inches. The other comment about lead, because we're talking about radioactive isotopes, and the further up we get the decay decay chain is the radium, and it's the radium scale, and we've often found that plates out in stainless steel. Underneath the rubber lining in places. So you might have, some people might not have picked up the subtleties. You've still got the chemical properties are the same.
Yes.
But you've also got the radiological properties. So you need to understand both the chemical properties and the radiological properties.
Yes.
And that's something that can be quite challenging.
And just one further comment on that subtlety is that radium typically is quite easy to detect because it has very penetrating gammas, so you don't miss them very easily. The lead and polonium and other stuff can go under the radar very easily, but yeah, that's good. Thank you.
The other thing that I'll just say is where there's a lot of disturbance, and the best example for that is shower rows at home where you've got the scale, it doesn't plate out in the pipe, it plates out where it's got that sort of
diffuse flow.
Diffusion and that disturbance. So that's another area where we've often found things in industrial plant.
Yep, it's no small job ahead.
I don't think I need the microphone. Thanks, Mike. Just in terms of the hazard, is the greatest hazard inhalation of the dust? Because I didn't get it.
When you
what was the greatest hazard?
I think I would say inhalation is probably the most concerning pathway. Is it? I wouldn't say it's necessarily dust. It could be, because they're potentially going to be things like water jetting, so you can cause mists and other things that can occur as well. And certainly aerosolizing and doing other stuff can occur. I'd suggest that absolutely is an issue. However, I'd suggest it's a reasonably easy to manage issue with PPE or other processes such as extraction fans or positive pressure type concepts for PPE. I'd suggest where people are quite lax is that ingestion pathway comes down to how well are you managing your hygiene. So you walk out of that area that's got sludge all the way through and you walk into the office to do something or to go to the toilet or whatever, you wash your hands and do other things, but unless you're slopping your boots around and getting that stuff off, if you look at, you can physically look at some of these guys and they've got crap all over them, ingestion probably is a bigger pathway as well. The absorption and injection, I'd suggest, are probably quite insignificant compared to those two, but I'd suggest both inhalation and ingestion are big pathways. I'd be betting on inhalation being the biggest. If you didn't manage it, inhalation would be the biggest, no doubt. Yep.
Well, thank you very much, Simon.
Very good. Thank you.